Probstats kids, this is Dr. Callahan with Week 15 Monday. How are you guys doing? I hope you had a wonderful week. Go ahead and pause the video and answer the following 3 questions for your warm-up blog for Week 15 Monday. All right, you guys, so here is the warm-up and the brain teaser, and can you figure out what is the missing number here? Well, if you look at it, 17 and 13 gives you 30. 17, 7, 6 also gives you 30. So 11, 5, and what number will give you 30? And that will be 14. So that is the answer because 25 and 5 is 30. 12, 7, 11 is 30. So there you go. All right, you guys, let's go ahead and get started with today's guided notes. It looks something like this. It is 2 pages front and back. This is the first page, and this is the back of that. So let's go ahead and get started with it. So when I saw you guys on week 14 Friday, we started talking about Hamiltonian or Hamilton's path and circuit. And so today is the second day of that. So we're going to start off with the traveling salesman's problem. It's a classic problem in which a traveling salesman is trying to determine the cheapest route that passes through each of the several cities, returning at the end of his trip to his hometown. So let's go ahead and talk about this. A Hamilton's path, similar to an Euler's path, instead of going through each of the edges and making sure that you only go through the edges once, a Hamilton's path in a graph is a path that visits each of the dots or vertex of the graph once and only once. And similarly to a Euler's circuit, a Hamilton's circuit is a circuit that visits each vertex of the graph once and only once. However, it must start and end at the same point. So then let's fill in the blank. Euler circuits and path. Euler equals touch each vertex, or edge of the graph exactly once, and by definition must touch every vertex, can touch more than once depending on the degrees. Hamilton can only touch each vertex exactly one time, and it doesn't require to touch every edge. All right, so let's go ahead and fill out this chart. Hamilton circuit path versus Euler circuit and path. For each of the following graph, use our definition of Hamilton-Euler to determine if the circuit and path of each type are possible. So let's take a look at graph number 1. For Euler's, and you might actually just try it on your own. So for Euler's path, you have to go through every single edge once and only once, but not retrace anything. Oh, in this case, it does work. Actually, it says no, but hold on a second. I'm pretty sure I did. Let's try that one more time. So edge, 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 and edge. So yes, I'm sorry about that. Circuit, it's also a yes. I mean, this is silly. If it's gonna be an Euler circuit, it's definitely an Euler's path, duh. And it didn't start at the same path. Now let's try the Hamilton's path. Hamilton means that you can only touch the dots once. So let's see. Once, okay, so far so good. Oh, perfect. It works. Now, did I end up at the same point? Yes, I did. So yes, 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 and yes. Now let's try graph number 2. Okay, so let's see if it meets the Euler's path. Awesome. It does meet the Euler's path, but it didn't start and end at the same point, but that's okay. Is it a Euler circuit? I don't think so. Unfortunately, no, because it ended and started at 2 different points. Now let's see if it is a Hamilton's path. They started here, touch the dot, touch the dot, touch the dot, touch that. So yes, it is a Hamilton's path, but it is not a Hamilton circuit because I started and ended at 2 different points. Pause the video and go ahead and try graph 3, 4, 5, and 6. Okay, here are the answers for graph number 3. It is an Euler, it's not an Euler's path. If I start here, I go here, 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 and here. Actually, it looks like it worked, but maybe I recrossed something. Let me try it one more time. Let's see, start here, 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 here. Oh, you know what? I'm not crossing this part, so it's not an Euler circuit. But could it be a Hamilton's path if I start at this vertex, this vertex, this vertex, this vertex, this vertex, this vertex? So I did start and end at the same part. So no, no, but yes, yes for Hamilton. Pause the video and answer question number, graph 4. All right, let's go ahead and take a look at this. So for the Euler's path, you will have to start here. Let's see. There we go, there we go, there we go, there we go. So you did start and end at the same part. And again, this one's a yes. I'm not quite sure why it says no, because if it's an Euler's path, it's always if it's going to be an Euler circuit, it's always going to be a path. Now let's go ahead and check to see if this also has a Hamilton's path. Touch the point, touch the point, touch the point, touch the point, touch the point. So yes, it is. But unfortunately, it did start and end at 2 different points. So now what I want you guys to do is pause the video and try graph 5 and 6. All right, let's go and take a look at the answers. All right, so for number 6, it is only a Hamilton's path. And for that, it's because if you go from this part, this part, this part, this part, this part, this part, and then this part. So you are touching all of the points, but unfortunately, you would not be able to connect all of the edges, or at least touch all the edges, because this edge right here is left behind. All right, so what do you notice with the relationship between a graph that has Euler circuit and path and have a Hamilton circular path? There is no relationship. I mean, unfortunately. In general, there are no theorems to determine if the graph has a Hamilton path or a circuit. Unlike Euler's, where you have the degrees and you count the edges. Here are some helpful hints. Number 1, for Hamilton circuit path, vertex of degrees 1 or 2 are very helpful because they represent the required edges to receive or reach the vertex. Second example, Hamilton circuit is A, B, C, D, and A. So we're going to follow the same notation order for a circuit, but with a different start. This is a distinct Hamilton circuit, a different order of vertices from left to right from the same standing vertex, reverse order, and counts. So let's see over here. So for the same Hamilton circuit, you follow the same notation order for circuits, but with a different start. If you look at it, here is A, B, C, D. If I start with B, so here is B, C, D, A, B. Okay, so I went to all of the vertex or all of the dots, and you start and end at the same point. Now, similarly with that, if I were to start at C, I will go to D, A, B, C, still end with C. And then similarly to that, you can also start with D. Now, if you have a different order of vertex from left to right, from the same starting vertex, reverse the order count. So A, D, C, B, A. So here we're starting off with A, D, and again, you're going opposite direction, counterclockwise, C, B, A. And here's another set of different options of how to go about finding it. Okay, so with that said, we're going to go ahead and move on to the next part of this. Okay, let's go ahead and go on to this part here. Complete the graph. Complete a graph within vertex in which every pair of distinct vertices is joined by an edge. One key properties of K sub n is that every vertex has a degree n minus 1. And just remember that every pair of distinct vertices is joined by an edge, and that edge is symbolized by K sub n. The number of edges in K sub n has n times n minus 1 divided by 2 edges. Of all the graph with n vertices and no multiple edges or loops, K sub n has the most edge, and there are n minus 1 factorial distinct Hamilton circuits in K sub 1. So for example, what is the question for K sub 8? Well, if I go ahead and follow this, remember your formula is going to be n times n minus 1 divided by 2. So in this case, it'll be 8 times 7 over 2, which is 56 divided by 2, which is going to be 28. So 28 edges if you have a vertex. How many Hamilton circuits are there? Well, to find the number of circuits, you will have to use this formula right there. So we will do 8 minus 1 factorial. So with your calculator, that's 7 factorial, which is 7 times 6 times 2, or 5, 4, 3, 2, 1. And that's 5,040 different methods of circuits. All right, let's go on. The way to graph any graph whose edges have numbers attached to them, and the weight are the numbers on each edge. So let's go ahead and take a look at the question here. So take a look at this diagram. Answer the following question based on the graph shown below. Find the weight of AB, which is the number of edges. As I'm looking at this part right here, the number of edges is going to be 38. Find a Hamilton circuit that starts with edge AB and give its weight. So if I start off with AB right here, plus BC, plus CD, plus DA. What that means is I take the 38 plus 22 plus 8 plus 12, and I will go ahead and add them together, which gives me a total of 80. And that is going to be the weight for the Hamilton circuit that starts with edge AB and then end with DA, because it connected or it touched every single vertex of this path, of this diagram. All right, you guys, now that we're done with this, next part I want you guys to do is go ahead and go to my Padlet board and answer the following questions. So I have a link right here in green, or you can go ahead and scan this QR code. And the question is, our last day of school is June 9th. Today is week 15. Last day is week 21. We have approximately 6 more weeks together. Question one, are there any habits you would like to modify during this time to provide one life-changing moment this school year? And if not life-changing, perhaps profoundly impactful to you. 3, what are you excited for in the summer? And last one, which classes do you need to raise your grade in? Make sure you answer these 4 questions on this Padlet. If you're not quite sure how the Padlet works, you just go to this green link and it will take you to the Padlet right here. You see the plus sign, go ahead and click on the plus sign and you're able to respond to it. All right, let's go back to this then. Okay, our next part right here is a Desmos activity that I would like you guys to go ahead and work on. You can either use a QR code or the green link, but once you guys get to it, this is what it's gonna look like. You're gonna type in your name. My name's Natalia, so I type it in, click on go, and then you're just gonna type your responses on Desmos. 16 questions, click on next. And then what you're going to do is you are going to list the vertices and edges of the following graph. Once you go ahead and list them, like let's say whatever, then go on to the next question. There are 16 of them all together, and you can go ahead and draw this even and then explain this, okay? All right, you guys, as always, oh, you know what? I kind of forgot one more thing, sorry. So I have one other thing I need you guys to do. This is your exit ticket. So what is a number that belongs to the top of this pyramid? This is also on your guided notes, so make sure you guys answer it. All right, well, I hope you guys have a wonderful week. And as always, stay safe and healthy, and I'll see you guys next time. Take care.